Okay, this lesson is on the slot method. So, got a quick quote from Thomas Edison there. I've not failed. I've just found 10,000 ways it won't work. And so the big thing here is it's going to be hard to find all the ways to make something possible. Um, and so there's going to be a lot of different strategies that we're going to have to use. And the slot method is a big one that's an extension of the fundamental counting principle. So the big idea for the whole first half of the course is really tools from probability really help you to make informed decisions and manage risk. The learning goal today is using the fundamental counting principle to calculate theoretical probabilities with more than two events. So in the last unit, we actually stopped at two events. So today we're going to be applying the slot method and using the slot method to calculate probabilities. We're going to use multiple cases and the indirect method as well. So warm-up question, applying what you learned in the previous unit, describe how you would determine how many ways there would be to have a password for the following lock. So the lock uses 5 slots, a letter for each slot, only capital letters. How would you figure that out? And we'll actually come back to that question. So enjoy this link. I'll put this video from Edward Snowden, John Oliver, outside of this video so that I don't infringe on any of his YouTube copyrights and make sure that we go back to that video, go right to his video rather than watching through this one. But it's a really interesting video on passwords and protecting yourself. Since it's not really practical to extend the dependent formula for a compound event for more than two dependent events, it's also not practical to do it to draw a bigger tree diagram. We need to develop a strategy that uses the fundamental counting principle, and we call that the slot method. Using this method, when asked to find a probability of a compound event, we will find the number of outcomes n of s, and we will also find n of a, and we're going to use slots, and it doesn't really matter if it's independent or dependent. We're just going to keep asking ourselves how many ways to make up this slot, to make up a compound event. So a quick example, just to extend from last unit. If you had a raffle in your class with 3 prizes, names are drawn from a hat and not replaced. There are 20 people in the class. What's the probability that you and your 2 best friends win the 3 prizes? So n of s is like the 3 different slots. So there are 20 ways for the first, 19 for the second, 18 for the third. N of a would be like you guys win the prize. So you could win grand prize, 3 people, 2 people for the second, 1 people for the third. And the probability would be 6 out of 6,840, or a very unlikely number, which is 0.0877%. Here's the password example back to the warm-up. So how many ways are there to have a password? So we do have 5 slots, and we've got all multiplied together, and that's really what the fundamental counting principle does. So we've got 26 ways for each. And so if you had that as your answer, and you can imagine this is why a tree diagram just becomes impossible because there's that many ways to do it. How many ways are there to have a password if you can only use each letter once? So you lose a letter every time you do a password. You can set up ask yourself the question, how many ways would there be for the first letter? Well, you haven't lost a letter yet, so 26. Now you've lost a letter, so 25, 24, 23, 22. And so that way it would be a little bit less, 7,893,000. And the probability the password is written without vowels, we just really take out those 5 letters and say how many ways can we put the first letter. So there's 21, and then 21, and 21, and 21, and 21. That is assuming that you can use letters more than once. Someone tells you that password is the word match, except I should say not necessarily in that order, because I didn't really factor in not that order. How many ways can the password use those letters? So again, we set up, back to the probability, because that was a probability question. So it's 4 million out of the 11,831,000, so it's 34%. 34% use no vowels. So you set up your 5 slots again. There are 5 letters now to choose from because there's only 5 that it could be. 4, 3, 2, 1. So those would be the letters match. How many ways to write it? 120. Password starts with M and ends with H. So you can set up the 5 slots, but there's only one way to start and one way to finish, and there's 3, 2, 1 in the middle. There's 6 total. And the probability, so if you can't just end it like that, you always have to divide by the total, and so it's 6 out of 120. In the last unit, we saw that there could be more than one way that an event can occur. So we recall the Denver Broncos question where they could win at home or on the road, so there's 2 cases. In that case, we need to calculate the individual probabilities of each case and add them together, or the total number of ways to do each case and add them together. But we have to separate the cases. So for an example, if we want to rearrange the letters in the word factor so that the vowels are together, so N of A would be the number of ways so the vowels are together. N of S is the total number of ways. So N of S we could set up first. So there's 6 letters, so we have 6 slots. And it's just 6 times 5 times 4 times 3 times 2 times 1. In N of A, there's multiple cases. So the vowels could be in the first 2 slots. They don't have to be, but they could be. And so if the vowels could be in the first 2 slots, they would go 2 times 1. And then we'd have four letters left over, 4, 3, 2, 1. Second case would be in the next 2 slots, so we'd have 2 times 1, and then 4 times 3 times 2 times 1. And we always set the restrictions first, because those vowels, they have 2 times 1 ways of going. Case 3 is similar. Case 4 is similar. And case 5 is similar. Put them in the last 2 slots, and then 4, 3, 2, 1. So they'll all be equivalent cases, but they're all separate cases in their own right. And so there's all the cases are 48, and so we actually have 48. We've got 5 times 48 cases, and so that's total 240. N of S is 720. The probability is 240 out of 720. Probability that, so now looking at an indirect method question, so we'll solve the question on the next slide, but just look at the question and see what the elements are to it. So you have a number password that has to be less than 10,000, created from the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, using each digit at most once. And what's the probability that it contains 6 or 8 or both? So you can only use every number once. The question is like, what's the probability that it's 6 or 8 or both? And the number has to be less than 10,000, which tells us that it has, like, you can only go up to 4 digits, but certainly you could use 1 digit, 2 digits, or 3 digits, or 4 digits. So that's like an issue there. So N of S actually has multiple ways to do it, which is something you got to watch out for. And then N of A actually becomes pretty complex. The number could use 6 in any slot, 8 in any slot, or 6 and 8 in any slot. And really, the question's complicated enough. So that second method tells me that the cases are actually becoming mind-numbing. So it's really important to think of a different way to count the number of ways, and it's really an indirect way. So the indirect way we're going to do it is just forget about 6 and 8. If we can forget about 6 and 8, we can do it a lot like N of S, and you'll see what I mean. So N of A is the total number of ways to contain 6 or 8 or both. N of A prime would be the total number of ways to use neither 6 nor 8. So 6 or 8 don't exist. So you just have less digits to work with. N of S is the total number of ways to have a number less than 10,000. So N of S has separate cases. So it's a 1-digit number. It can't be 0. So there are 9 ways to do it. Case 2 is a 2-digit number. You can't start with 0 because then 09 would be a 1-digit number. So there are 9 ways to do the first number and 9 ways to do the second. because you lost the first digit. So now you can use 0 in the second one. Case 3 is 0 can't be first again. So there are 9 ways to do the first, 9 ways to do the second, and then 8 ways to do the third because you've slotted 2 of the digits. Remember, there are 10 digits to work with. 0 is a digit, but it can't come at the beginning. And case 4 would be the 4 digits 9, 9, 8, 7. And so together they add up to the total number of ways to do it. If we think of a prime as a 1-digit number, now we just have that extra restriction. You can't be 6 or 8 either. And so a 1-digit number can't be 0, 6, or 8, so there's 7 numbers. A 2-digit number, the first one can't be 0, and none of them can be 6 or 8. And so you have 7 ways to do the first, and if you've put 0 back in but knock out 6 or 8, you actually have 7 ways to do the second. Because you've slotted a number here, so you've lost a number. You've lost 6 or 8, so that's now you're down to you're down to 7 total numbers. And you'll notice that like over here, it's just really 2 less. So you've already kind of set up all the different format for this. So it's 2 less for each case. So 3 digits, there's 7 ways to do the first, again, 7 ways to do the second, and 6 ways to do the third. And again, it's 2 less every time because you lost 6 or 8. And 4 digits, you've got 7, 7, 6, 5. And so total number of ways are 18, 20. If you did the probability of that's the probability you don't want. You actually want the 3,445. So you want 6 or 8 or both. And so the probability total is 65%. So 65% chance that you've got 6 or 8 or both of those numbers in a password. Here's some practice questions. I added some questions from the textbook that you can try. 5 students, 2 teachers pose for a picture. This is one where you have to do slots. And then using the slot method in multiple cases, calculate the probability you roll 3 6s if you roll 4 dice. So it doesn't have to worry about the sum of 4. We've done a lot of sum of 2 dice. But you're rolling 4 dice and 3 of them have to be 6s. A lot of these questions are not necessarily probability questions. They're just like the total number of ways. But that's one of the hardest things to do is just figure out the total number of ways.